Hello, my name is Neustroev, and in this video I'm going to talk about my paper on generalized optimistic Q-learning with provable efficiency. In short, this paper introduces a mathematical framework of sample efficiency analysis for a family of reinforcement learning algorithms known as optimistic Q-learning methods. In reinforcement learning, an agent interacts with an environment by performing various actions. Each action yields a reward and changes the environment's state. The agent wants to find the best possible course of actions, known as a policy. In this paper, we consider the case of finite state and action space, like in the example you can see on the screen. We consider an episodic learning environment. The agent acts for a given number of steps, h, and then the environment resets. We denote the number of interactions with the environment t and the number of state action combinations x. Normally, this would be the problem size, but we also allow the problem data to change over time, which means that the best possible action depends not only on the state, but on the time step too. And the total problem space is thus x multiplied by h. We would like our agent to learn the best policy, but we would also like it to happen as fast and as efficient as possible. There exist different measures of learning efficiency, and in this paper we use the total regret of learning. In each episode, we can define the optimal value, which is the best total reward the agent could have accrued. The total reward collected by the agent in an episode is less than the optimum, but as the agent learns, it keeps improving. The difference between the optimal value and the actual value of an episode is known as regret, and the total regret over all episodes can be used as the measure of efficiency. The lower is the total regret, the better is the learning algorithm. Ideally, we want the regret to grow slower than both time and environment size, in which case we can say that the agent uses the information from the interactions with the environment efficiently. Now, let's look at the existing reinforcement learning methods. They fall into two categories: model-free methods, which aim to learn the optimal values directly, and model-based, which build a model of the environment instead. Q-learning is a classic example of a model-free method. It is simple, easy to implement, and its time and space complexity are very low. Unfortunately, the regret of Q-learning grows linearly with time, so it is provably inefficient. Model-based methods, on the other hand, achieve provable efficiency, but require more time and more memory space to run. For a long time, model-based methods were the only provably efficient ones. Fortunately, recently, for a family of new model-free methods, efficiency proof have been done. We call these methods optimistic Q-learning methods. And as you can see from the table, they're efficient in their regret, time, and space use. All of these methods are variants of Q-learning. In Q-learning, the agent learns so-called Q values, which show how good an action is for a given state at a given time. The best policy is then easy to find. The agent just needs to use the action with the highest Q value. These values are initialized arbitrarily, and then they are updated based on the agent's experiences with the environment. As the number of interactions grow, the learned Q values converge to the optimal ones. Optimistic Q-learning methods are all based on the same principle, known as optimism in the face of uncertainty. It postulates that the unknown should be considered as good as statistically plausible. There are two ways this is usually implemented: by optimistic initializations, states we have never visited are thought to be good, and by action selection based on upper confidence bounds. We assume that the output of an action we have seen before is as good as statistically plausible. In optimistic Q-learning, the latter is usually done by adding a bonus to the Q value updates, which makes the Q values higher. It makes them optimistic. When we started working on this paper, we looked at the existing optimistic Q-learning methods to see how they differ from regular Q-learning. We found that all of the methods introduce the same modifications to Q-learning, highlighted in blue. For example, all of them use the same learning rate alpha you can see on your screen. At the same time, each method does different things as well. Most notably, the bonus terms can be substantially different. As a result, an efficiency proof for one of the methods cannot be easily transferred to another one. So we thought, can we introduce a common framework for the theoretical analysis of these methods? And the answer is yes. In fact, all of them can be generalized into a single algorithm, which you can see on your screen, and they differ only in their choice of the 5 hyperparameters. These hyperparameters are the exploration rate, the learning rate, the initial values, and the two bonuses, one for the upper confidence bounds based exploration and another one for the optimistic initialization. Next, we looked at these hyperparameters to see which of their properties are required to prove sample efficiency of generalized optimistic Q-learning. To keep the analysis simple, we have only considered the case of no exploration, but decided to add the exploration rate as a parameter for future research. So let us look at the parameters of our algorithm. First, the learning rate. All of the optimistic methods use the same learning rate. For regular Q-learning, two other learning rates can be found in the analysis as well. What is so special about these learning rates that allows for sample efficiency proofs? As it turns out, it is a simple fact that the initial learning rate is equal to 1. Intuitively, this means that we know that at the first visit, the initial Q values are overwritten and replaced by updates. The initial values do not affect the visited states, and these are evaluated based on the past experiences with the environment only. Is this enough? No. As it turns out, we need to impose some additional restrictions as well. For example, the updates are random, and to find the confidence bounds, we need to be able to quantify the variance of the updates. We do so by introducing a function zeta, which can be found if the learning rates is known. Similarly to zeta, we require two additional functions to exist. It is a more technical one, but intuitively it quantifies the regret propagation through the episodes. Mu, which we call the magnitude function, acts as a scaling factor. It quantifies how the regret scales with the problem data. These conditions on the learning rate are enough to reason about efficiency, but there are other hyperparameters. For the rest of the hyperparameters, we also impose some conditions, which you can see on your screen. Most importantly, we introduce a function theta, which represents how big the bonuses are. So these 7 conditions together bring us to the main contribution of this paper, which is the theorem you can see on your screen. It tells us that if all of the conditions hold, the regret is bounded by 3 factors: the problem size, the total effect of the bonuses B, and the estimation error E, which comes from the uncertainty in the updates. This is a simple yet powerful result, as checking the conditions can be rather simple. For example, let us consider a method known as UCB-H, or upper confidence bound Q-learning with Hoeffding style bonus. In the generalized terms, this method can be represented by the following combination of the hyperparameters. Using these, we can find the 4 functions introduced earlier. In fact, all of these functions are implicitly used somewhere in the efficiency proof in the original paper, but they're never given names or otherwise noted. Using mu and theta from the previous slide, we compute the effects of bonuses and estimation error and the total regret bound. In the regret bound, the middle term dominates the other 2, so we omit them, leaving us with the bound that we have seen earlier. Moreover, we know that this bound is explained by the bonus choice. Next, I would like to show how this framework can be used to design new reinforcement learning methods. Let us consider the learning rates we have seen earlier. Can we combine all of them into one? Yes, we can. What if we use this new learning rate? Is the resulting method provably efficient? We introduced such a method, and we call it UCB-H+. It is a simple modification of UCB-H, which also uses a slightly different bonus. Similarly to UCB-H, we check all of the conditions, and you can see it in more detail in the paper. Then we use the functions mu and theta to obtain a regret bound, which allows us to conclude that this method is indeed provably efficient. Moreover, we can see that the coefficient omega can be tuned to balance the time complexity, T, and space complexity, Hx, of the problem. We also tested this new algorithm on 2 problems, and you can see the results on the screen. To conclude, optimistic Q-learning is a promising research direction, as it is both model-free and sample-efficient. We introduced a framework that simplifies the regret analysis of optimistic Q-learning and showed the driving factors of the regret. Next, we would like to expand this framework, for example, by introducing dithering, or random exploration, by adding more complex environments such as continuous state space, and by finding not just sufficient, but also necessary conditions for sample efficiency of optimistic Q-learning. Thank you for your attention. And if you have any questions, please send me an email.